Retina. The retina envelopes almost the entire inner wall of the posterior chamber of the eye. It is in this part of the eye that light is registered, setting up nerve excitations which are transferred to the sensorial regions of the brain, where the stimulus is interpreted. The retina is a thin membrane of about 0.2 millimeter thickness, which light can traverse with ease. The microscope reveals that the thinness of the retina is no indication of its complexity, for at about 1,500 times the magnification, a transverse section may show up to 10 distinct layers. The function of the various layers is not too well understood, although each has been the subject of thorough study. Fortunately, a complete knowledge of all the retinal layers is not required for this discussion, but a few are of extreme importance. In Figure 3 is shown a simplified schematic drawing of the retinal layer. It can be seen that, contrary to one's expectation, the light of focus upon the retina must pass through the entire layer before reaching the elements of sensitivity. This fact seems to be no barrier to good vision, however. In the foremost posterior region of the retinal layer are situated the so-called rods and cones, both of which have been considered the receptors of the visual organ, although at least one outstanding authority claims that only the cones are recipient bodies. The rods are shaped like thin cylinders, while the cones are bulged at one end and taper off at the other. These sensitive elements are highly concentrated, but are not equally distributed over the entire retina. In the general region of sharpest vision, called the macula lutea, or yellow spot, wherein is located the fovea centralis, the cones widely outnumber the rods. The number of cones in the macula has been estimated as approximately 150,000 per square millimeter. There are actually no rods to speak of in the macula, and so it is easy to calculate the probable diameter of the cones in this region as around 2.6 millimeters. Or no, 0.0026 millimeters. As counts are made farther and farther away from the foveal region, the number of cones per square millimeter decreases. The number of rods increases, and the total number of sensitive elements per unit area decreases. At the extreme periphery, the cones again become predominant. The cones also become larger outside the fovea. The total number of cones in the retina is of the order of 3 million, while, according to some estimates, there are up to 20 times this many rods. It will also be noted that the retina is depressed in the foveal region, but it is questionable whether the thinness of this portion of the retina can in any way account for sharp vision. Some hawks have much better vision than man, in spite of considerably thicker retinas. Since the retina covers the entire inner posterior wall of the eyeball, the angular scope of the human vision for both eyes is almost 180 degrees in the horizontal plane. One can test this by stretching his arm out sideways and observing the wiggling of a finger while looking straight ahead. The vision at such an acute angle is not distinct, but it does exist. Actually, the angle of a sharp vision is very small, since high visual acuity is limited to the tiny cone-packed oval-shaped fovea having the approximate dimensions of 0.24 millimeters by 0.3 millimeters. The angle subtended in sharp vision is about 1 degree. Beyond this, vision is indistinct, and for the eye to cover an area subtending an angle greater than 1 degree, giving the impression of sharpness, it must scan the area continuously, such as happens when viewing a motion picture screen in the theater. We are not conscious of the scanning operations and are led to believe that we have a wider field of sharp vision than is actual. The visual path. The excitations created photochemically in the receptors are conveyed through the retinal structure by a complex system of ganglion cells and nerve fibers. The cones of the minute fovea lead out to the optic nerve, bundled by single fiber. However, since the total number of nerve fibers in the optic nerve leading to the brain is only about 100,000, it is obvious that each of the several million light-sensitive elements does not have a one-to-one correspondence with the brain. Actually, large groups of rods and cones are connected to a single nerve fiber, and this is further complicated by a most intricate visual path through the retinal layers. This can perhaps help to explain why retinal stimulation at one point often gives rise to adjacent disturbances. Light action on the retina. Although the more classical and more widely acknowledged theory, the duplicity theory, states that both the cones and the rods respond to light stimuli, they are said to react quite differently in the most functional aspects. To begin with, according to this theory, the rods are very much more sensitive to light than the cones, and at very low levels of illumination. Only the rods will respond. These levels are lower than the so-called cone threshold, which is around 0.001 lumen per square feet. The absolute threshold below which even the rods are non-responsive is about 0.00001 lumens over square feet. At low illumination levels where rod vision is predominant, it is generally assumed that no hues can be seen. Thus the expression, "all cats are gray at night." This is known, however, as night vision or scotopic vision. However, in spite of the fact that this assumption is well rooted in the field of physiological optics, the reader is warned not to accept it by any means as final. Some evidence points to the fact that the rods are not recipient bodies at all, only the cones functioning in this capacity. The cones, according to the duplicity theory, have a special function in creating sensations of hue in daylight or during photopic vision. As we have noted, the cones are tightly packed, especially in the foveal region, and so they are also responsible for our distinct vision, partly explaining why visual acuity is at a maximum under daylight illumination levels rather than at twilight. During night vision, when the cones are inoperative, the point of a sharp focus on the retina automatically shifts from the fovea to a region where rods are present. The exact mechanisms of visual excitation is not completely understood. There is even the possibility that what is thought to be understood is incorrect. However, it is known that there are light-sensitive substances present in the retina which decompose photochemically, the ionic products of the decomposition acting indirectly as a nerve activators which create coordinated impulses that are sent to the brain via the optic nerve. One of the light-sensitive substances of the retina was discovered as far back as 1876 by Bohl.
I've made so much money.
This substance is known as visual purple, or rhodopsin. It is a complicated protein, purplish in color, quickly bleaching when exposed to light. The visual purple is found in the rods and in other parts of the retinal layer, but not in the cones. Experimental evidence of a corresponding light-sensitive material in the cones is scarce, but comparatively recently it has been disclosed that a substance called iodopsin is present in them and may be responsible for their stimulation. Dr. Wald of Harvard has also isolated and identified 3 color pigments in the retinal cones, which no doubt are in some way connected with the photochemical cycle of vision. The pigments isolated by Dr. Wald are astacine, color pigment of a boiled lobster, xanthophyll, coloring matter in egg yolk, and carotene, the pigment of the carrot. These compounds are related to the vitamin A structure, which we shall see is of fundamental importance in the photochemical retinal processes. The bleaching of the visual purple is directly proportional to the intensity of the light stimulus and to its concentration. If we call the light-sensitive substance S, under the influence of light, two decomposition products, A and B, will be formed. Thus, since in the presence of light the supply of S is rapidly diminished, there must be a reverse reaction taking place to restore the supply. It has been found that the ionic components A and B are recombined in the bloodstream provided there is an ample concentration of vitamin A. Actually, one of the decomposition products of S is thought to be vitamin A, and the other substance known as retinine. When there is a surplus of vitamin A, it is natural to expect the above reaction to be reversible. However, a more satisfactory explanation of the cycle has been given by Wald and Clark. They have viewed the decomposition and reformation of rhodopsin as taking place in two phases, one of which is reversible. The primary action of light upon the rhodopsin is the formation of retinine, visual yellow, and a protein. The retinine then forms vitamin A, which reacts with protein substances to reestablish rhodopsin, or the retinine reforms rhodopsin directly. This is shown in the equations below. The sensitivity of the eye is dependent upon the concentration of S. S is light. The higher it is, the more effective a weak stimulus will be. However, the actual stimulation of a nerve fiber is not thought to be caused by one of the byproducts of the breakdown of S. Resting in the receptors, according to Hecht, is a substance which we shall designate as R. The R substance has a tendency to change a nerve irritant, which can be represented by the letter I. But the reaction R to I takes place only in the presence of A and B, and will not take place at all until the concentration of A and B has reached a definite value. There are certain justifications for Hecht's postulation. It explains why there is a lapse of time between light stimulation and sensation. It also contributes to the explanation of retention of image, so important for the production of motion pictures. It also explains why the eye is a poor criterion for judging duration of light. For judging duration of light flashes, and should discourage photographers from attempting to determine whether a shutter is properly operated at, say, 1/200th of a second by comparing the flash duration produced by directing the camera toward a source of light while the shutter is tripped against, say, 1/100th of a second. Day and night vision. As stated previously in the duplicity theory, it is assumed that the retina contains two almost independently functioning receptors, the rods and the cones. The rods are more sensitive to weak intensities than the cones, but the cones are responsible for color vision. It is likely to expect, then, that data determined for the eye would be influenced greatly by the level of intensity at which measurements are made. Since in one case we have operating rod vision, scotopic or night vision, and in the other cone vision, photopic or day vision. That such distinct sets of data are obtainable is the chief factor in support of the double receptor concept. For example, it is well known that the eye does not have a constant sensitivity for all the wavelengths through the visible spectrum. The eye of a normal observer is far more sensitive in the central part of the color spectrum, green-yellow, than it is at the red or blue extremes. However, the exact placement of the maximum of sensitivity is a function of the light level at which the test is conducted. In Figure 4 are shown two visibility curves giving the central pattern of the eye response to various wavelengths from 4,000 to 7,000 angstrom units. Curve S being drawn for scotopic visual levels. fainter than 10.4 candles per square foot, and curve P being drawn for photopic visual levels, brighter than 10 minus 1 candles per square foot. It will be noticed that there is a decided shift in the wavelength sensitivity when the illumination levels are changed. At high intensities, the eye is more yellow sensitive than at low intensities, where the sensitivity maximum lies in the green. This shift in sensitivity is well known Purkinje phenomenon, and it is the peculiar action of the eye which makes the almost non-perceptible light from a dark green safe light quite effective for film inspection once the eye has become dark adapted, and hence the scotopic vision is in full action. Another measurable difference in retinal sensitivity for scotopic and photopic vision is the change in sensitivity across the retina itself. Figure 5 shows a curve representing the variation in sensitivity across the retina for photopic vision. The foveal region shows a maximum sensitivity with a smooth decrease towards the periphery. The blind spot corresponds to the point of entry of the optic nerve in the retina, where there are naturally no receptor elements. In figure 6, a similar curve is shown, but this time for the scotopic eye. It will be seen that the fovea shows the lowest sensitivity under low levels of illumination, and this is supposed to be due to the absence of rods in this region of the retina. It is interesting to observe that the curve in figure 5 follows rather closely the cone distribution across the retina. Adaptation. We have had occasion to use the term adaptation before defining it. It will not be necessary for our purposes to present the mass action principles involved in the adaptation process, but suffice it to state that the eye becomes adapted to various light intensity levels after certain periods of time, chiefly because of an equilibrium that is established between the formation and destruction of the retinal visual purple, and because of the involuntary changes in the opening of the iris. The latter factor can account for a small amount of the total adaptation only, although in photographic literature one is often led to believe that the iris is the only factor in operation. When one speaks of the fully dark adapted eye, reference is made to scotopic or rod vision, while the expression daylight adapted eye refers to the photopic or cone vision. Visual acuity. The ability of the eye to distinguish fine detail is chiefly dependent upon the perfectness of the lens system and upon the limits of resolution imposed by the structure of the recipient elements of the retina. Actually, the seat of distinct vision is limited to a very narrow angle, 1 degree, corresponding to the coverage of the fovea. As we have seen, the cones in the fovea are closely packed, and each cone has a direct nerve fiber leading to the optic nerve. By reflexive action, the eye focuses its image upon the fovea, not upon the optical axis as might be expected. Outside the bounds of the foveal image, the sharpness of vision is greatly reduced, as can be seen from the diagram in figure 7. The measurement of visual acuity is no easy job. The test procedure has to be carefully planned and many factors properly considered in evaluating final results. Visual acuity varies widely in different individuals, and results obtained with any given individual are greatly dependent upon adaptation, type of test object, glare, nature of surroundings of test object, etc. But one outstanding fact is that the visual acuity and the ability to distinguish variations in intensities are closely related. A black object on a white surface is readily distinguishable, but as the background is made more and more gray, the discrimination becomes increasingly difficult. In testing for the minimum perceptible contrast, large areas are employed, one of which is varied in intensity so that the barely perceptible brilliance difference is established for different adaptation levels. Typical results are shown in figure 8, which LA is the adaptation luminosity, and LB is the luminosity of the outside ring of the test object, and LO is the luminosity of the center disk of the test object. From these data, it is evident that contrast discrimination increases with luminosity. Thus, we can expect that visual acuity will vary with adaptation level and have a maximum at high values. The work of Lithgow, as well as others, shows this to be true. In Figure 9, a curve gives the increase of acuity with luminosity. For this work, Lithgow used the international test object shown in Figure 10, which is a broken circle having an opening equal to 1/5 of the outside diameter of the circle. By orienting the test object at different angles and asking an observer to judge the position of the opening, a measure of acuity is obtainable. It is interesting to note that the results vary according to the color of light being used. Sodium vapor, yellow for example, gives higher values than incandescent lamplight. With red light, visual acuity is worse than for white, and for blue it is very poor. For a complete study of visual acuity, see the bibliography at the end of this article. Resolving power of the eye. More commonly used in photographic circles than visual acuity is the resolving power of the eye. This property of the eye is distinguished from acuity in that it is a measure of the eye's ability to distinguish fine detail when there is a large contrast between object and background, whereas acuity involves small brightness differences of extended surfaces. It is generally assumed in photography that the resolving power of the eye is a rather fixed property equal to 100 lines per inch. We shall see that the value is much higher in many cases and certainly not a fixed property. When viewing an object, a very much reduced image is formed upon the retina. How much detail the eye can discern will depend largely upon viewing distance and the size of the original. Using as a basis the concept that the eye can resolve two lines or dots which are separated by 1 minute of arc, objects to be recognizable cannot be placed farther away than 3,440 times their longest linear dimension. At this distance, no detail in the subject can be registered, but the subject itself can be distinguished from other objects. The question is, what is there about the makeup of the eye that limits the resolution to this relatively low value? It would simplify the explanation if we had to consider only the limiting factors of the retina. However, the problem is considerably more complex since resolving power is influenced by imperfections of imagery, type of test objects, illumination conditions, retinal limitations, quality of light source, and other factors. For present purposes, we need not consider all these factors. We know that a point of light is never focused upon a focal plane as a true point, but rather it is focused in the plane with the light spreading outward from a bright central image. The distribution of the light in a typical case is represented by the curve in Figure 11. If 2 points of a light close together in the subject form distribution patterns of this type on the retina, the overlap of the border intensities tends to cause the points to visually merge together. The 2 points can be distinguished provided there is a difference of 10% in the intensities at points A and B. The effective distribution of light is shown in Figure 12. Along similar lines of reasoning, it can be shown why it is possible to see a much finer single black line on a white background than it is to distinguish between two black lines separated by a space equal to the width of the lines. This will also clear up the apparent fallacy between the least perceptible image and the least separable image. It has been shown that the eye can easily see a small wire against a bright sky in which the angle subtended is but about 4 seconds of arc, while the resolution of a series of parallel lines under best conditions never approaches this low limit. The explanation for this is seen in figures 13 and 14. The dotted lines in figure 13 represents the overlapping light distributions from the white borders surrounding the black line. The effective light distribution on the retina is shown by a solid line. Thus, a black line of 0.5 Greek mi, so it's probably 0.005 width is perceptible, since the difference in brightness is about 10%. Now, in the case where two black lines are separated by a white space, the situation is considerably changed. In figure 14, the white center line forms a distribution pattern that overlaps with the borders of the distribution curves of the outer white surroundings. The final light distribution follows the solid line. Here we have two black lines of 2 mi width separated by a 2 mi white space, resulting in a retinal image that is not perceived as two lines, but as one. In this case, the variation in intensity between the central white space and the adjacent black lines is less than 10%, clearly showing that 2 mi separated lines are not as effective as a single 0.5 mi line. In the above cases, ideal subjects of maximum contrast have been considered. However, as shown conclusively by Cobb and Moss, visual acuity is depreciated when the contrast is lower. We have already seen how acuity is affected by luminosity, but actually it is a function of both luminosity and contrast. For example, had the subject in figure 13 been a light gray line on a white background, we would find that in order to perceive it, the width of the line would have to be considerably wider. With a gray having a reflection factor of 0.5, the line would have to be about 1 mi. Accommodation. One of the surprising functions of the eye is its ability to adjust its focus according to the distance of the subject viewed. This action is accomplished primarily by changes in the curvature of the crystalline lens, but the ability to do this varies widely in individuals and is progressively lost in all individuals with age. Ability to accommodate the focus is largely a matter of training and practice also. Some optometrists are treating patients by exercises designed to improve accommodation without the use of glasses. Certain investigations point to the fact that accommodation is mostly a matter of mental interpretation of the retinal image. It is thought in some ways that optical aids destroy the will to see, making the use of mental accommodation sluggish. As a result, we have such things as progressive myopia, in which persons afflicted with minor malfocus of images, although getting relief by corrective spectacles, find that periodic changes in correction are required. The problem of accommodation is far from thoroughly explained. It is an interesting study, but one which does not have considerable bearing on the discussion here. Binocular cooperation. In the normal person, both eyes form retinal images which are blended together in the brain to produce a single impression. Each eye gives the observer a different view. It is this fact that accounts mostly for our binocular depth perception. The movement of the two eyes in perfect unison is the result of persistent practice and is completely automatic. When the eyes become fatigued, however, the binocular cooperation is affected and one experiences double images. The movements of the eyes are simultaneous in two distinct senses. They move in unison when scanning an object at a given fixation distance, and the angle of view of each eye changes for different points of focus. The latter is referred to as convergence. Visual mechanism in relation to pictorial photography. No effort has been made in the foregoing description to present a comprehensive discussion on the visual mechanism. Actually, even at the risk of superficiality, the treatment has been made brief, since only by reference to original papers and standard texts can a thorough understanding of the many problems and complexities involved be achieved. Sufficient references are given at the end of this article for those who wish to pursue the study further. However, it is hoped that this meager insight into the operation of the visual mechanism will provoke a more intelligent outlook in any consideration of a visual and photographic correspondence. It is at least clear that the visual process is not a simple one. The eye has developed in man by many evolutionary steps. Just how and why the present stage of development has been reached cannot be stated, but it is certain that other arrangements have different visual properties could have been possible. In the present stage of development, an imperfect optical image is produced upon a complex layer of cells which are stimulated by photochemical reactions. The nerve excitations are registered in the brain by completely unknown processes, although it is known that the mental state of the observer, his memory, and numerous psychological factors enter into the final act of perception. The external world, as perceived in the brain, is indeed a different world than focused upon the retina. With a slight knowledge of the visual process, we are better prepared than to discuss the ideology of using the visual factors in the formation of pictorial photographic criterion. First of all, we must dispel the assumption that it is necessary to have a visual criterion of some sort in pictorial photography. It is very possible that the development of photography could follow in channels quite removed from a perfect photographic visual correspondence. Indeed, we shall see that the present tendencies of photography are definitely opposed to such a relation, even though the majority of advanced workers assume that a correlation between the photographic and visual images is the thing being striven for. But the efforts now being expended are, for the most part, opposed to the assumption. When it is known what is necessary to effect the visual correspondence, it is likely that the criterion will be abandoned as undesirable. We have seen that the eye is a reasonably good optical instrument. On the other hand, we know that it is no match for the optical refinement of modern photographic lenses. In the very beginning, then, it appears as though the visual-photographic relation is at odds. The question is, in what way does the difference between visual imagery and camera lens imagery cause a breakdown in the criterion? We shall assume modern anastigmatic lenses to be perfectly free from number 1, chromatic aberration, 2, distortion, and 3, defects in sharpness. In comparison to the extent of these factors in the optics of the human eye, it is safe to make this assumption. The eye suffers from all 3 defects, which, of course, is not surprising. When we view a scene, there are no immediate evidences that these defects are present. However, each can be demonstrated. The classical proof of the existence of chromatic aberration in the eye is the appearance of a purple light viewed from a distance. 2 distant images, one red and one blue, are seen because of the difference in focus of the extremes of the spectrum. That distortion in the eye is present, can be evidenced by viewing a rectangular pattern and noticing that the lines at the edge of the field of view appear to be bowed. The lack of perfect visual sharpness is clear from our inability to see in objects at a distance minute details that we would know to exist from having seen them at close range. Now, if a photographic image is to duplicate the visual image, should we not expect the photograph to have distorted lines at the edge of the field, a sharpness rendering not unlike that of the eye, and edge effects caused from chromatic aberration? It was shown by Proctor and Ames, that painters often incorporated such defects unknowingly in arriving at their results. Many famous paintings show deliberate use of distortion. Barrel distinction is very evident in Israel's The Day Before Parting, which is reproduced in Figure 15. By introducing chromatic aberration in the form of color edge, Blanche Ames has produced marked depth effects in paintings. Millet, in many of his paintings, edged foreground objects with reddish colors and put bluish edges on background objects, as shown in Figure 16. The feeling of depth perception is improved by use of a lens having optical aberration about the same as the eye. But while reproduction from a pictorial standpoint seems best when it embodies the visual defects, modern practice is to try to produce lenses without optical aberrations. This is, of course, desirable from a scientific standpoint. However, so long as the trend exists, it seems that all attempts to relate the results obtained with such lenses to visual likenesses should be dropped.